In this video, I'm going to discuss the actual arrangement of electrons as we understand them today. And this is called the quantum mechanical model of the atom. So the atom is actually a cloud, we call it. So we've learned about Bohr's models and the idea that electrons have a certain amount of energy based on where they're located, and Bohr hypothesized that there were these specific energy rings where they existed, and to this point that's what we've been looking at. But now I'm going to go further into detail, sort of explaining these shells in terms of what we now know as sort of a cloud model. So essentially what we understand the atom of now is that electrons have a probability of existence. There is a region of space around a nucleus where an electron is likely to exist, and we call that the cloud, or the probability cloud. And that electron doesn't exist in that cloud until we observe it there. Now, these clouds are sort of organized in a very sort of predictable mathematical way. But to just kind of give you a better idea of what this means, I always like to use the example of a fan. So if you're looking at a fan and you don't try and focus in on any of the blades, it looks like a blur. But if you try and focus your eye on one of the blades and follow it, then you can actually see that blade moving around. And that's kind of how an electron is. There's this blur of space where it is likely to exist, and then once we look and we observe it, we see it in one position. So I'm going to spend this video talking about the organization of the cloud. So it's a little bit more complex than Bohr's model, where we said there was 2 in the first energy level and 8 in the second and 18 in the third. And so now we're going to kind of go a little bit deeper and look into the complexities of this. So those energy levels that Bohr kind of came up with were called the principal quantum number, or the principal energy level. So the energy level is given a number, a 1, a 2, a 3, and it's called the N number. And that you can actually see on the back of your reference tables. It's listed as the N number. And within each one of these energy levels, there's sublevels. So there's S, P, D, and or F sublevels. So I kind of like to think about it like a football stadium or a basketball stadium, right? If you go to an arena and you have a ticket and it says that you're on the first deck, you're on the ground level, or you're on the first deck, or you're on the second deck, you're in this section, right, and you're in this seat. So think of it like that. So the principal quantum number is, what level you're on. The sub-level, the S, P, D, or F, is sort of what section you are sitting in. And then within each sub-level, there's a certain amount of seats, okay, or there's a certain amount of places where an electron can go. So for each sub-level, there's a different numbers of orbitals based on its shape, and the shape is what sort of gives the atom now its cloud model. So if we look at the sub-levels, you can see here's an S sub-level. An S sub-level is like a sphere. A p sublevel is actually made up of 3 different orbitals that look like little hourglasses, and they're in 3 different dimensions. You have one in the x and one in the y, and then one in the z that sort of pops out at you. The d has actually 5 orbitals, and now each orbital can hold 2 electrons. So s sublevels have 1 orbital that 2 electrons can fit in. The p sublevel has 3 orbitals, 2 electrons can fit in each. The d has 5 and the f has 7. So if we look here, the organization of the orbitals. So an s, remember this is a sublevel, has 1 orbital and therefore can hold 2 electrons. Oops, this goes kind of in the wrong order. Therefore can hold 2 electrons because each orbital holds 2 electrons. The p sublevel has 3 orbitals, those 3 little hourglass things we looked at, and each one holds 2 electrons, so you can have a total of 6 electrons. Then the d has 5 orbitals, and therefore 10 electrons can be held. And the f has 7, and therefore 14 electrons can be held. So the first energy level only has 1 sublevel. It has the S sublevel, and therefore only has 1 orbital so it can only hold 2 electrons. So that's where Bohr's idea comes from, of only 2 electrons in the first energy level, because it only has that one s orbital. So this is how we write it. This 1 right here stands for the energy level, the s indicates the orbital, and the 2 indicates the number of electrons that are in that orbital. Alright, so then if we go to the second energy level, recall from Bohr's model it can hold 8, so this is why it can hold 8. It has an s and a p orbital, or a sublevel, and each, you can remember the s has 2 and p has 6, right? So S has 2 electrons in its one orbital. P has 3 orbitals with 2 electrons each, so a total of 6 electrons, and so it can have a total of 8. So if we look here, this is how we write it. 2's here, 2s being the orbital, 2 being the number of electrons, and then the little 2 here, that represents the energy level, and then the orbital, and then the number of electrons. Alright, the third energy level. So the third energy level has 3 sublevels. It has S, P, and D, and therefore has all the S, P, and D orbitals. Remember, 2 electrons can fit in the S, 6 in the P, and 10 in the D, and that's where we get that 18 total electrons in the third shell from. So you can see the 3's represent the shell number, the S, the P, and the D tell you the sublevels and the orbitals, and the 2, 6, and 10 tells you the number of electrons. Finally, we have the fourth energy level. So the fourth energy level can have S, P, Ds, and Fs. And there are 2 in the S, 6 in the P, 10 in the D, and 14 in the F. So actually we can hold 32 electrons in the fourth energy level. And you can see here the 4 representing the shell number, the energy level, S being the orbitals, and these exponents here being the numbers of electrons. Now what happens if we get above the fourth energy level? There are not many atoms that have that many electrons, so we only go up to the S, P, D, and F. There is no other orbital. Those are the only 4 kinds that we have. So if we get to an electron that has a 5th or 6th or 7th energy level, it will only have S, P, Ds, and Fs. We'll actually run out of electrons before we'll need another orbital. Now, the orbitals don't fill up in a neat sort of predictable order. So we're going to talk about the rules of how to express where the electrons are existing, and there are 3 different rules to kind of show what I've overviewed so far. So one of the things, because of this 3-dimensional sort of cloud shape of all these orbitals, is that when you get up to higher energy levels, they actually overlap one another, so they don't fill in sort of the predictable normal order that we see, but they always fill from the lowest energy to the highest energy. But it's not some nice, neat order that we would think it would be. So for now, you'll be given a sheet like this to help us to predict the order of fill. And we will learn in topic 3 about how to memorize it. So you will not be given this on the test. It'll be a lot easier. You'll know how to do it by the time we get to the test. So you can see you just kind of follow the arrows. It just kind of snakes around here. And the first S orbital fills first, and then the second S, and then the second P. And that's all predictable and seems like the correct order. But then we get to the third S fills, and then the 3P, and before the D orbital fills of the third, the S orbital of the fourth energy level actually overlaps it before we get to the 3D. So that's when things start to get a little out of order, the D sublevel being behind the S of the next shell. Okay, and we'll practice these in the next video. Okay, so electron configurations and orbital diagrams are how we arrange and represent and show the electrons as they fill the various orbitals. So there are 3 rules to follow. The first is Aufbau's building up principle. And so Aufbau's principle means that electrons enter the lowest energy level first. And that's observed by following that sort of pattern that we just saw that's a little out of order. Then we have Pauli's exclusion principle, and we've already talked about this. We know that only 2 electrons can fit in an orbital, and so this helps us to represent electrons as well in an atom. Now, another thing about Pauli's exclusion principle is he says that electrons also spin. They have different directions. They spin in opposite directions. And when we draw an orbital diagram, we're actually going to represent it by drawing a box to represent the orbital and drawing arrows to represent the electrons, and one electron will spin up and one will spin down. And that will make more sense in the next video where I actually teach you how to do orbital diagrams, but just keep that in mind. Then the last rule of electron configurations and orbital diagrams is Hunds Rule. And Hunds Rule says that electrons don't pair up until they have to. So electrons will not share the same orbital space until they have to based on their order of fill. So in the next video, we're going to learn to write orbital diagrams, and I'll kind of review all these rules, and then I will give you some examples.